All right, so welcome to the Center for Transportational Logistics Research webinar. And I'm Vijit Roy. I'm a faculty at the Indian Institute of Management, Ahmedabad, and also co-chair of the center. We're very excited to have with us today Dr. Marve Udur. She is a faculty at the School of Mathematics at the University of Edinburgh. And today her research talk will be on incorporating service reliability in multi-depot vehicle scheduling. And several of her work uses very fascinating optimization frameworks, including chance-constrained approach, which she is going to talk about today. A bit about Dr. Marve. She's an associate professor in the School of Mathematics at the University of Edinburgh. And she obtained her PhD from the University of Wisconsin-Madison, her bachelor's in industrial engineering, and her BA in maths from Boğaziçi University, Turkey. Her main research area is optimization under uncertainty, primarily for discrete optimization problems with a variety of applications, scheduling, transportation, healthcare, telecommunication, and power systems. She also serves on the editorial boards of several prestigious journals like OR Letters, Omega, and Infor. She's currently the vice chair-elect of the Informs Computing Society and serves on the Committee on Stochastic Programming and is former vice chair of the Informs Optimization Society. So that's about Dr. Marve. We are very excited to have you with us today. And we have a variety of participants from all over the India, probably across the world too. So welcome to all of you, and thank you, Dr. Marve, to present this work in our forum. So we are very excited to have you.
Thank you so very much.
Yeah, I give the floor to Zoom all to you, and participants do put your questions in the chat. I'll be also moderating that. So thank you so much. Please go ahead.
Sounds good. No, thank you so very much for the kind introduction, Devjit, and also for the invitation in the first place. I am so very happy to be here today, and I know it's a bit late there, so thank you so very much for everyone attending. I'm very pleased to see a large number of attendees in the room. So yeah, it's a pleasure to be here, and especially I have some familiar faces in the audience as well, some close friends from my community. So yeah, very happy to be here. So hopefully maybe at the end we will have a chance to chat for a few minutes. So during the talk seminar, if you have any questions, feel free to just unmute and ask if you will. I'm more than happy to take questions along the way. I don't have to go through all the slides. The important thing is to give you guys an idea about what this problem is about and inspire maybe some of you to look into similar problems from the practical perspective, but also maybe leverage some of the similar methodological modeling and solution methods in your own research related to some other problems. All right, so today I will like to tell you a little bit about, I will explain shortly. I think I see on the chat the very first question. By the way, because I'm sharing my iPad screen, you will also be seeing my color scale. I apologize for that. I cannot hide it. So today I would like to tell you a little bit about this MDVSP problem, which is standing for multi-depot vehicle scheduling problem. And this is a very well-known problem in transportation area. There's a vast literature I will quickly review shortly. But what we are trying to do in this work is especially we would like to incorporate some insurance for practitioners that things are going to work well when you implement this schedule in the operational stage. You will have some service reliability for your customers. And how we are going to do that? We will try to do this thanks to this guarantees that come along with the chance constraint model. And before I move any further, I would like to acknowledge my wonderful collaborators, Margarita Castro, who is an assistant professor in PUC, Chile, and Professor Amer Shalabi, who is a professor at the University of Toronto. Okay, so MDVSP, we are going to talk about multi-depot vehicle scheduling problem. And as we all know, and especially this group in particular, transit agencies, they do face several decision-making problems with the goal of providing a high-quality service to their customers, right? And they also, of course, would like to do that, if possible, at a low cost. And in that regard, they are facing many problems, decision-making problems, and some of the most important ones, as you see in the screen, which they usually solve in this particular order. And in that regard, among, I would say, the tactical problems, the vehicle scheduling is a very important one because it directly impacts the service to their customers, but also it incurs high costs. So this is an important planning problem that they have at hand. So in that regard, in this research, we are going to consider the practically relevant version of the vehicle scheduling where we have multiple depots as many agencies, large agencies, they do. All right, so here's basically a loaded slide. I will walk you through it slowly, which describes our problem at hand, this multi-depot vehicle scheduling problem. So first of all, let's go through this step by step. We do have a given timetable at hand. So that is an input to the vehicle scheduling problem. So in other words, we are given a set of trips that come with their associated start times, as well as their, say, estimated duration. So I have on the right a quick example where I have these 1 to 8 trips at hand. Each comes with their earliest start time. So you cannot, this is the timetable start time, and you are supposed to start this trip, say, preferably at time 5. But of course, if there's a delay because of certain things, you have to start maybe sometime later. And then here's the estimated duration of the trip. Say it will take 5 units of time. So this is the timetable given to us, a set of trips that we need to take care of by assigning our vehicles to handle them. So the agency also has these multiple depots, hence the name multi-depot VSP, but each depot comes with a certain capacity, which is basically how many buses you can locate simultaneously at the depot. So depots are capacitated, and here in the example, I'm talking about 2 depots, say K1 and K2. And as it is commonly done, we are considering a homogeneous fleet of buses for our transit agency. And also, as I said, in the timetable, we are given the travel times of the trips, how long they will take estimated. But in our model, we will consider stochastic options for them. And also cost parameters, maybe let me come back to it shortly. So what is the goal of the MDVSP problem? So our goal is to assign buses to depots, as well as assign each trip to exactly one bus, so that, in other words, in our schedule, vehicle schedule, each bus will get to be assigned a sequence of trips that they need to do in this order. So in my quick example here, say the first bus is going to be assigned to depot 1, and then it is going to do this, what we call a deadhead trip. It's going to travel empty for a while, and then say it's going to do trip 1. It's going to do a little bit of more deadhead trip to come to the start location of trip 3. It's going to do trip 3, trip 4, trip 2, and then it will come back to depot that is assigned to K1. So practically, one thing that is important is buses must return to their assigned original depot at the end of the day. So this is something that agencies, they do desire to have. So with respect to the cost, so the main problem is clear. So what we need to do is for each bus, we need to find an assigned depot, and then we need to assign them a set of sequence of trips to do during the day. And each trip needs to be assigned to exactly one bus, only one bus. So with respect to the costs, what we have is, of course, various things might lead to a cost. And in that regard, as you can imagine, operational costs will include most notably the fuel, or if you have electrical buses, electricity consumption type of costs. And then for each bus, we have a fixed cost, which might very well incur the salaries of the drivers. And also, as I mentioned, like these deadhead trips, traveling empty, it is also quite costly. So you also want to basically minimize the deadhead time. But various cost aspects you can easily fit into our optimization model. All right, so first let's talk about there's no stochasticity in the world, and let's talk about the deterministic MDVSP, which is, I would say, vastly studied in the literature. It is basically a very famous problem, and in that regard, there are multiple approaches to address this problem. One of the most successful one has been this flow type of formulation. So you can actually create, as in this example, a multi-commodity network flow formulation for deterministic version of the problem, in which basically you create, first of all, the nodes. What type of nodes we have? For each depot, in my example, I have 2. I create 2 copies, one for starting the sequence of trips, the other one is ending the sequence of the trips. And then also for each trip, say in this example, I didn't want to draw all 5. I have 5 trips at hand. For each, I am putting a node in my graph as well. And then arcs correspond to basically compatible orders of trip pairs. So for instance, I put this arc going from trip 1 node to trip 5 node, because with respect to the timetable and the locations, I am able to do with one particular bus, I can do trip 1 first, and then immediately after I can successfully, based on the timetable, I can handle trip 5. So these are compatible, for which we put an arc there. And then the commodities will be the buses, different types of flow, if you will. And then when you create and solve this problem and then obtain a flow formulation. For instance, formulation will lead to this blue flow and then pink flow, which are going to be assigned to my blue bus and then pink bus. And basically the flows will give you the trip sequences assigned to the buses. And then beginning and end locations will be telling you the assigned depots of the buses. So this is a very successful approach. And how you do this is you actually, in practice, you bury this methodologically into a branch and cut algorithm and do some other enhancement tricks, but this is very successfully applied. There are some other approaches in the literature, as I mentioned, but because we are going to consider stochastic variant, unfortunately, some of them will not be directly applicable to ours, but the network flow formulation is going to be amenable to our stochastic variant. I will explain it shortly. So now let's think about if you have this MDVSP problem, what we would like to do is specifically consider a stochastic variant because uncertainty is inevitable in practice, right? And in that regard, we would like to incorporate the most notable source of uncertainty, namely the travel time uncertainty. So travel times, they are not specifically known as these fixed numbers. They actually have these possibilities for future. All right, so in that regard, if you look at the literature, what type of deterministic approaches, despite that you have uncertainty in practice, unfortunately, practitioners usually rely on deterministic approaches, which do have, unfortunately, some serious drawbacks. So if you're a transit agency as a practitioner, what you might be considered doing to incorporate this uncertainty, basically you have historical data of travel times, but what you may want to do is simply use a statistical estimate and then rely on a deterministic model as in the flow formulation that I showed you. So in that regard, one thing that is most natural to think about is just use historical data, put the average travel times as if they are going to happen in practice, and then solve the deterministic model with these average travel time estimates, which would, of course, give you an implementable schedule. But unfortunately, if there is large delays, large variability, uncertainty in real life, then this schedule will be highly sensitive to that. It's not going to perform well, as we will also see in our benchmarks in the numerical section. But actually, practitioners, transit agencies, as far as I know from my especially domain expert collaborators, they claim that they are not using this simple average estimates. They try to hedge against uncertainty, these delays in practice a bit better. In that sense, to hedge against uncertainty, they put some overestimates. For instance, they put, instead of the averages, they put, say, 75th quantile of their demand distribution data so that they overestimate travel times, hoping that their schedules will be more robust in that sense. But what this leads to is, unfortunately, the schedules that they end up with by using these overestimates is going to be costlier. Moreover, what is important is, unfortunately, they are not going to necessarily lead to a guaranteed acceptable service quality, which we will measure. I will define it shortly, explicitly, on-time performance, what they use most commonly in practice. So although you design something that will perform well, you cannot guarantee that in practice they are going to perform well. Okay. Plus, with respect to overestimation, like this parameter, how much I should overestimate? Should I use 75% quantile, 80%, 90%? What is the right number? If you want to rely on this approach, you need to do some tuning effort, which could be costly as well computationally. Okay. If you look at the academic literature now, we also see some attempts trying to properly more incorporate uncertainty into the MDVSP models, but unfortunately, to the best of our knowledge, that hasn't been done properly yet. So there are some works, of course, which are trying to penalize these delays if they happen, but unfortunately, the majority of the works, what they do is they try to incorporate uncertainty, but unfortunately, in their models, they ignore that delays actually will propagate. They will accumulate, but instead they just penalize individual delays. Accordingly, it's not going to be that appropriate of a model. And there's one other or a couple other works that are, instead of considering the schedule design in the first place, they are basically trying how to modify the schedule in real time if delays occur. But unfortunately, this is not practically a relevant approach to design a schedule in the first place. Plus these schedules, vehicle schedules, as I will also mention shortly, they will be used for at least few weeks, if not up to a couple months. So these real-time adjustments, they will be highly impractical if you want to do that often. So what we are hoping to do is we are trying to design a model that will properly account for travel uncertainty of the future and will lead to some reliable, robust schedules so that we don't need this too much of a real-time adjustments in reality. Okay, so this is the slide actually how our work got whole started. So this is the real practical motivation that led to our chance constraint model. So basically, we were looking at this Toronto Transit Agency, TTC, and what they are doing is TTC actually, they publish this report every day. Every weekday of the week, basically they publish this type of a chart showing that what was their on-time performance, we will define it again shortly, but what is their target service quality measure? And 100 is the best you can reach, but they target, say for the buses, they target 90%, but then every day they release actually how successful they've been in that regard. So they are basically very clear about their performance. Customers can see that on their website. For instance, on May 15, when I prepared this very first slide at the time, they only are able to reach to 80% despite that they target 90%. So what is this target? So this is what we are going to talk about, this on-time performance, which is very, very commonly used, measured across the globe for transit agencies. So this is basically what is written in the bottom here, footnote. So what we want is most of our buses to depart for their trips on time. But on time here in the bottom part here, on time is defined, say for trip I, if there is a targeted start time coming from the timetable as you should start at this time. In practice, it's okay to be slightly early or slightly late. So what they do is they give you a time window, and each agency has a different definition. They basically give you this timetabled SI time, start time, minus a lower bound plus an upper bound. So for instance, for Toronto, this is 1 minute, this is 5 minutes. And they say if a bus, instead of starting this trip I on time exactly SI, if it starts 1 minute early or 5 minutes up to 5 minutes late, this trip happened on time. So this is on time departure. So you have this on time departure window. And basically, what you want is most of your trips, and this is your target for that day, operational day, you want 90% of your trips to start on time with respect to this window definition. And another example, now that I'm in Europe, it is from Europe. So this is from London Bus Transit Agency TfL. And instead of daily, they are a bit more hesitant to report their exact performance measures. So they report it quarterly, and this is one of their latest quarterly reports. And here we see that this is too small, but I will write it here. They define on-time performance very similar, but they have minus 2 minutes plus 5 minutes defined to be on time for departures. And accordingly here, they are looking at exactly the same on-time performance. On the bottom, highlighted red here, you see 79.5 is pretty much similar to what Toronto has been able to achieve on May 15. They also want to reach, say, 90-95% on-time departures for their trips. But unfortunately, in this quarter 3 of the last year, they are able to reach only 80%. So this is basically our key point in our model. So in that regard, what we would like to do is we would like to create a model for which, for our schedules, this targeted, say, 90% on-time performance is guaranteed. So that's what we are hoping to do. Okay, our goal is to design these vehicle schedules. And if you think about the practice, this is important because we are going to create a planning problem. So in that regard, it is important to acknowledge that these vehicle schedules, they will be employed. They are usually employed by agencies for up to 2-3 months, but sometimes weeks, but sometimes months. They are going to stick into the same vehicle schedule, but you will be operating for many, many days. So in that regard, it may not be possible to maybe reach this target of, say, 90% on-time departures for your trips every day. But what we want is most of the days, we would like to reach this target, which motivates our chance constraint model. So it is inevitable that some operational days, if you are going to use the same schedule for 2-3 months, you may not be able to reach your target of 90%. But if we are reaching it most of the days, we are happy. This is a good schedule, and chance constraint modeling will help you to get such a guarantee. All right, so putting everything together, this story, this motivation, in this work, our particular contributions it starts with proposing a proper stochastic MDVSP model. And in that regard, our goal is to develop cost-efficient vehicle schedules with the guarantee of on-time performance. But as I said, it is too much to hope that you will hit your target on-time performance every single day. So if we are hitting it for most days where we are using this schedule, we are hitting our goal. This is what we are going to especially guarantee with our chance constraint model. In addition, fairness is a big concern now, and transit agencies, they seem to start caring about it, really. So in that regard, we will also have in our model explicit assurance that fairness will be satisfied across the routes. Because in order to create a good schedule, if you just maybe get your on-time performance guarantee for most of the routes and you're always disadvantaging a few set of routes, this is not fair, right, to those passengers from those regions. So we also would like to explicitly model fairness. And how are we going to do that? We are going to propose a chance constraint model. But this model, unfortunately, it's going to be a two-stage model, if you will. But in the operational stage, especially, we have some integer decision variables, which will be making the solution method-wise very challenging of a model. And if you look at the literature, basically, there are only a few things that you can try, which are not computationally as helpful for our problem here. So that's why methodologically, first and foremost, we are going to develop an exact solution method, which is based on branch and cut algorithm. And this is going to be able to solve, say, small to medium size instances exactly, so that we will, first of all, be able to justify the value of our chance constraint model in the first place. And in that regard, as time permits, I will show you different cut families that we used in this methodology. But if you want to go to a practitioner, I say, use this exact method, they will say, no way, it's going to work because I have hundreds of trips, if not more. Exactly, you cannot run this algorithm in an efficient manner. As such as their desire, we will give them a heuristic to make them happy, but we are optimizers, so we are going to give them an optimization-based heuristic. I will detail you shortly what is the main idea, but basically we are going to divide our big scheduling problem into smaller components. And for the smaller components, we are going to employ our exact method, and then we are going to bury this into overall a Lagrangian decomposition-based framework. But we will still be leveraging our exact method, which can solve smaller size instances in a heuristic to be able to attack practical size instances. All right, so this was basically our game plan. So let me tell you, as time permits, as many details as possible quickly. So first of all, before I introduce my chance constraint model, the scheduling part is going to be clear to everybody, but we need to formalize the service requirements a little bit better. So here's an example, and we are in the stochastic setting. So I'm using a similar example with 8 trips with their earliest start times, and their estimated durations. But in real life, there's uncertainty. So these durations will not be necessarily these numbers that we are given. So rather, in this tiny example, I will illustrate 2 possible future travel time scenarios, yellow and purple. So you can think of it for this grid, say each cell takes 1 unit of time to cross. And then if in the yellow scenario, if you go through one of these patched areas, then you are going to increase the time by half. So these are going to lead to some delays, increase travel times for the patched areas in 2 different yellow and purple scenarios. So in the pictures here, you see 2 different schedules. For instance, in this one, the bus 1 is assigned here and it's going to do these trips, whereas bus 2 is going to handle the other trips. And then the other schedule is looking a bit different. So let me tell you what we care about with respect to service requirements. So as I mentioned, we want this on-time performance. And in that regard, on-time, having a trip I actually happening on time is defined by this time window, right? So in Toronto, they are using 1 to 5 minutes. In London, they are using -2 + 5. So if trip I actually in your schedule, in reality, when uncertainty is realized, if it occurs, it departs at this time window. In this time window, this trip is happening on time. And the first service requirement we want is there is this parameter given to us by the practitioners, and we want at least this many trips out of all to start on time with respect to this definition. So for instance, in my example, I have 8 trips in total. Say they gave me the 7. So I want at least 7 out of 8 trips to start on time in my schedule. The second thing, as I mentioned, is fairness that we care about. So a similar parameter is given per route. For each route R, I want this many trips at least to start on time. Say maybe you want 50% of every route to start on time. In my example, you can think of it as, say, each pair here, say it's a route, and say among them, each having 2 trips, you want at least one of them to be on time for fairness reasons. But then now here's the chance constraint part where it comes to play. So when we say service requirements are met, we want both the OTP and the fairness conditions to be satisfied. But then there are these scenarios, right? Yellow scenario and purple scenario. So with respect to the scenarios, we are also given a third parameter, which is this epsilon here, which says at least this portion of the scenarios, these service requirements should be met. Say in my example, maybe epsilon is 0.5, then I have 2 scenarios, then I want at least one scenario to meet both of my service requirements, otherwise this schedule is not acceptable. So in that regard, it's hard to put the numbers together, but I will just tell you at a high level, this first schedule, if you check these scenarios, then you are going to see that actually in the yellow scenario as well as the purple scenario, you violate at least one, if not both of these requirements. So this is not a feasible schedule for us with respect to this chance constraint condition. But on the other hand, the second schedule, if you check it, every of the conditions, you are going to see that it is indeed a feasible schedule. All right, so let's put these things, all of them together into my 2-state chance constraint model. So this is a very, very simple model if the problem definition is clear. But maybe before, let me pause for a second. If anyone has any questions about
there's one question over here. The question is, how do the results compare for the average time versus median of the travel time?
We are going to talk about it. So if you want to solve a deterministic model, you can put whichever summary statistic that you want. To be honest, in our comparisons, we didn't use median. That's maybe another good one to try. But I'm going to show you results where we use the average and then say 75% quantile. But I will hopefully convince you that whichever summary statistic you use, you should not rely on a deterministic model. You should consider possibilities for future.
Mm-hmm.
But median can be different than the mean for sure.
I don't see any other questions right now.
Okay, wonderful. Let me know if anyone else has any question.
Hold on, it just came up.
Okay.
Another question on animation. On an average, are all routes considered equivalent length due to refueling, charging?
Not necessarily. So this is an input. So in our computational tests, we are going to put a similar number of trips, but in reality, routes might not necessarily have similar characteristics, if you will. And in that regard, you can also, as you wish, you can also modify these, for instance, especially fairness measures, right? So if a route consists of fewer trips, maybe you need to have a higher parameter there because it might hurt that region. Maybe it's a poorer region. It might hurt that region more. So it's flexible, but for us at the moment, it is just an input. So I don't necessarily care about how they look like. It's flexible.
I think a related question is, I think you already answered, is the model applicable for milk run only? And the answer is not. Just any flexible routes. Yeah.
Yes.
All right. Maybe we'll take one more before you continue. How do you determine the model parameters when you have all trips under a transit agency, which are important?
It should come from them, right? It depends on their own preferences. But for instance, this epsilon, the chance constraint related ones, I would say it should be at least maybe 95% of the time. Like this should be relatively high, right? Most of the days you should be feasible with respect to meeting these requirements. But of course, if you reduce this number, as we will see in the results, you will end up with basically cost reductions. But then these ones again, in our experiments, we just made up some numbers, although we talked to some practitioners and got an idea roughly. But of course, the higher, the better. But you might end up not guaranteeing feasibility in that regard, right? But these parameters are totally, again, up to their own preferences. But one thing you could do is you can potentially do some sensitivity analysis and then give them a full picture, and then they can pick, okay, maybe this is better considering everything with respect to my own budget and preferences.
Sure. We can continue, Margaret.
Okay, sounds good. So then let me show you the model quickly here. So the model, as I mentioned, is going to rely on this multi-commodity flow formulation. Remember, we have nodes for 2 copies of the nodes for the depots and nodes for the trips, and then arcs are representing basically what is compatible. If you can do this trip right after this trip, you have an arc, right? So then the variables are basically this multi-commodity version of the flow variables. So here xijk means if you are going to do by a bus trip I, right after you will do trip J by a bus that is assigned to depot K. So then this variable will be taking the value of 1. So then the cost is basically, everything is a bit compactly represented for the sake of the presentation, but if you make such an assignment, there is going to be a cost associated with it. This could be, again, the operational fuel, electricity cost, maybe the cost of assigning the bus to depot. The costs basically are given to the arcs in that way. And then for the constraints, for each, sorry, my apologies. So for each trip J, basically you look at all possible assignments, and among those, you should pick exactly one. So each trip must be assigned to exactly one bus, which should be assigned to exactly one depot. That's what this is doing. And then for the depots, we have capacities. They can handle this many buses in total at time. So in that regard, we are looking at basically these variables are saying whether you are starting a trip at the depot K, and then by a bus assigned to depot K. So if these are ones, it means these buses will be allocated to depot K, and you cannot allocate more than BK many. So the rest, basically, they are just flow balance. If you are gonna, in the flow model, if you are entering a node, you should exit a node. So these are just flow balance constraints. And then the last set of constraints are just enforcing this practical consideration by the agencies that if a bus is assigned to depot K, it has to come back to depot K at the end of the day. So you cannot start a trip at K prime, but by a bus assigned to depot K. So that's for this specific requirement. Okay, so this is basically the vehicle scheduling part. If you basically find any solution feasible to this set and you get your X solution, it describes your vehicle schedule that you can use. But as I mentioned, our primary goal is to ensure service requirements are met with high probability. That's why we need the one more constraint in blue here, which is going to be our joint chance constraint. So what is this saying is, here we have the random vector, which is describing for all the trips, basically their random travel times, their durations. And this probability is taken with respect to this joint distribution of all of these random variables. And what is this saying is, whether our schedule, candidate schedule X, under the realization of this, basically under the scenario that's going to be realized with respect to travel times of all the trips, whether it belongs to this, say, set describing that our service requirements are met, OTP and fairness. I will explain shortly in detail. But if the schedule is feasible with respect to meeting our service requirements, then this is going to be a good thing. And how often you want to have this good case that you meet the service requirements, it is at least with this probability. Say maybe this is something small, so this is maybe 95% of the time, 95% of the operational days, you want to meet these service requirements. So how are we going to basically describe this, enforce this chance constraint? We are going to do a scenario reformulation. So instead of working with the continuous space, we are going to generate as many possible future scenarios for the basically realizations of the trip durations. And we are going to introduce one binary variable z, indicating whether this is going to be a good scenario or bad scenario. So specifically here, z will be equal to 0, meaning it is a good scenario as opposed to that we are used to. So be careful. So if z is equal to 0, our schedule for that scenario, it is going to belong to this scenario feasible set that I will show you in the next slide, meaning that this is a good scenario. Service requirements will be met under that scenario S. So then if you look at this one, this is going to become now the discretized chance constraint, how many scenarios could be bad? So if z is equal to 1, it's going to be a bad scenario. If you sum over all the z's that are equal to 1, number of z's that are bad, it cannot exceed this many scenarios. So for instance, if I have 100 scenarios, but this is 0.05, then I only at most 5 scenarios I accept as bad. 95 of them must be good, meeting our service requirements. So let's see the service requirements. So this is, if you will, the second stage problem in that case. So what do we have? So now I'm talking about a specific scenario and what is it going to be, whether it is good or bad with respect to the constraints describing the service requirements. So remember, there are two main things in the service requirements, OTP and fairness. Let's start with the first one. So first of all, we are introducing these V variables for scenario S. So VIS is equal to 1 if trip I starts on time in this scenario S, given our schedule and the realizations of the durations, trip durations. So then this is how many trips start on time, good ones, and we want by the OTP requirement, if z is equal to 0, this is a good scenario. In that case, we want at least this many trips out of all to start on time, so that many v's should be summing up to 1. So same condition we have for fairness reasons for the routes. Now for each route, if you just sum over the trips that belong to that route, this many of them you want to be good, you want to start on time if z is equal to 0, meaning this is a good scenario. So then we have more variables. So these y variables are denoting the exact actual start times of the trips under this schedule and for this scenario. And accordingly, if basically this trip must start on time, v is equal to 1, then you want this start time to be in this window between, it is given start time minus lower bound plus upper bound. If v is equal to 1, this trip must start on time. It needs to start time needs to belong to this given interval. And given again the practical strategies to help with the schedule to meeting service conditions, we also consider these variables for expressing a bus. So you can speed it up a little bit up to this given limit to basically save some time in the durations of the trip. So we have those variables, how much we can speed up, how much we want to speed up. And accordingly here, we are going to basically link them to our actual start time decisions. So this is saying that if a bus is going to do trip J and right after it's going to do trip I, then the start times of these guys should be related. Basically, this is the start time of trip J, duration of it, plus the travel time from J to I, minus how much you can speed up, save this time. If you are going to do this, basically J, and then right after J, you will do I. This is going to be equal to, 0. So this term is going to disappear. So this is going to be at least the eligible start time for trip I. So you link basically the selected arcs, you link their start times accordingly. So this is our full chance constraint model, the scheduling first stage part in the previous slide, and this is the operational second stage part, if you will. So how can we solve this model? So the difficulty is we have some binary decision variables, of course, continuous variables as well, but we have mixed integer or mixed binary recourse here, for which the available efficient decomposition algorithms, unfortunately, they are very limited. So we needed to do something new ourselves to solve our model a bit better. So before I move on to the methodology, any other questions about the model and the problem?
Yeah, there's one question, Marve, on your slide 8. The question was, how do you tweak the formulation, I guess, if you have multiple starting points, example, trucks arriving at the terminal to pick up the boxes? So I think it's all about multiple starting points. Can the model be able to accommodate such?
So if a bus needs to go to a certain place during the day, we treat it as another trip that needs to be done. But primarily our main depot assignments are for where the bus is going to start the day, where it spend the night, and where it has to go back at the end of the day. So that's, again, practically what they want. So that's the only thing about this third index there, which is the depot assignment of the buses. But if you have any other special tasks to do during the day, we will treat them as additional trips, additional tasks, if you will.
Okay.
I don't know whether this answers the question.
Yeah, and the follow-up question was, you have a plus or minus sign for the start time.
Yeah.
And how much do you allow it for minutes?
So it's not minutes. So for these things, so this is the suggested start time in the timetable. Say maybe this should be 3 p.m. And then say in Toronto, what they accept as the allowed like on time start is if you do basically -1 minute plus 5 minutes. If you start by between 14:59 and 15:05, this is on time start for this trip.
All right. There's a follow-up question by Pratik. He's asking, what is scalability of the model compared to deterministic setting? I think you answered that.
Yeah, getting there.
Yeah. We'll continue then. And
okay, so I need to rush here for a bit for the methodology. I will try to just give you a high-level idea. Don't maybe get into so much details, and then maybe results will be more interesting for the audience. But at a high level, we have a difficult problem with some integer variables in first and second stage problems, and large scale, hopefully, we would like to solve. So we need to decompose it. This is too big to solve in one shot if you give to your favorite solver. So we apply the decomposition algorithm. But since we have some integer decisions, binary decisions in the second stage problem, we cannot rely on pure Bander's decomposition. If you are familiar, we needed to design our own cuts for the algorithm, our own logic, basically, for so-called logic-based Bander's decomposition. But overall, the main idea of the decomposition algorithm is you are going to solve this so-called master problem, which is going to give you a candidate schedule described by the X, and then it's going to just give you some guesses that these scenarios are going to be good for the schedule, these scenarios are going to be bad for the schedule. But then in the second part of the algorithm, you shouldn't rely on what master problem is saying because it's just a guess, it's just a candidate. So for the scenarios that basically master problem claims that they are good, service requirements should be satisfied, you should go ahead and check it. So for any schedule, for the given schedule, for any scenario that master problem claims to be good, z is equal to 0, you are going to go ahead and then solve our second stage problem for that candidate schedule to see whether indeed it is feasible or not, whether service requirements are satisfied or not. If they're all satisfied, this candidate schedule is good. You take it as your optimal solution. Otherwise, you need to return some information in the form of logical constraints, cutting planes, to kill that guessed solution so that master problem will give you a better solution that will lead to feasibility in the future. So let's try to imagine applying this algorithm. But of course, I'm not going to get into details, but because of the integer variables, you need to bury this into a branch and cut framework, but I'm not going to detail that. So in the start of the algorithm, we need to initialize our master problem, which has our vehicle scheduling multi-commutative flow formulation, plus we have these scenarios, right? And among which at most this many can be bad scenarios. So we saw this one. But of course, before we solve this one, we want to strengthen it. We don't want, for instance, for the first time, master problem doesn't know anything about disease. It can tell you, you know what, all of them are zeros, all of them are good scenarios, right? So this is not a good start. So we want to strengthen it from the get-go a little bit. So we add some valid inequalities, which are based on some simple ideas that certain things will from the get-go lead to infeasibility. We give this information to our master problem. So basically, what we look at here is, for each scenario, we look at the trips, and then we find pairs. If you do them consecutively, that will for sure lead to some delays. So here's an example. So we look at this set, which is basically the scenario compatible set. So the details are not important, but if you pick any pair of trips from this set and do them consecutively, they will be fine. They will not necessarily lead to delays. But if you schedule any pair of trip I and then right after that j outside of this set that we define, this compatible set that we define, we know for a fact that the second trip j will be delayed in this scenario S. So we know from the get-go which ones will be delayed with respect to our scheduling. So accordingly, we can add a constraint like that. We can sum over the ones that are going to for sure lead to delay here. And this is how many maximum of them you have the cardinality of the set pretty much, which is going to serve as a big M in this constraint. But if we sum over these ones that are surely known to lead to delays, then we can do the following. If this is a good scenario, right, then z is equal to 0, meaning at most this many should be delayed for sure, right? So we can at least tell the master problem from the get-go that some information, just do your choices wisely. Plus, because of the fact that we know every bus should be assigned to exactly one depot, we can even strengthen this constraint by summing over the depot options here. But that's roughly the idea. Just tell master problem from the get-go that certain things will immediately lead to delays, so prevent them to at least have a better candidate. And this was for all the trips. We can do something similar for each route, again, but this time using the fairness parameter for the routes. So this is how we start the algorithm. So then master problem gives you a candidate schedule, right? And then some guesses of the scenarios, which ones are good, which ones are bad. Next, we need to go to our sub-problem, and for each scenario that master problem claims to be good, we should actually solve the second stage problem and see whether it is good or not. Our service requirements are satisfied or not. If you recall, this was our second stage problem. So the good thing about this problem is our structure is simple, and we observe that we don't need to solve this as a mixed integer program. We can apply a greedy algorithm to solve this sub-problem, which is easy. So, but that's not the main contribution. So being able to solve this sub-problem via greedy algorithm, it's nice, it saves you some time, but it is also crucial for our cut generation idea. So we are going to rely on the solution of specifically this greedy algorithm to design certain cuts efficiently. So that's why what we care about this algorithm is more so for cut generation, not the solution time per se. But the main idea, I'm going to skip quickly, but the main idea is, given a candidate schedule, you basically start in the schedule and propagate from the beginning to the end of the trips and start every trip as early as possible. So you can basically easily go through the suggested start times, and then in a loop way, you can easily decide what time earliest each trip can start. So you can easily greedily solve this problem. But as I said, that's not important, because the difficulty arises from the fact that we have an integer recurse problem for which the cuts should be logically generated. They should be correct, valid, and they should be strong. So, as I said, subproblems are easy to solve. We can apply our greedy algorithm, but nevertheless, we need some cuts that are going to be integrality based. So, in that regard, the first thing you can borrow from the literature, it's common knowledge, it's super easy to apply, is these so-called no-good cuts. What are they doing is, given a candidate schedule X, let me say X hat, if you look at the ones that are taking value 1, and put them as X's here into the cut, and you look at the ones in this X hat candidate schedule which are taking value 0, put their complement here, and then if you know that this is not a feasible schedule, it violates your service requirements for that scenario, you know that this thing whose cardinality is at most this number V bar, they cannot be all basically summing up to V bar because it's infeasible. You can say, if this is a good scenario, if Z equal to 0, this left-hand side cannot be sum up to 1. You need to change at least one thing to potentially make it feasible. So these cuts are super easy to derive in that sense, but they are extremely weak because they are only cutting off this one particular exact solution. If you like, you can do better than that. You can strengthen it a little bit, basically pretty much removing this part, but they are still nevertheless quite weak. And the reason why they are weak is because they are actually looking at this whole sequence, all the vehicle schedule, and using that information to generate some cuts. But instead, if you want to do something better, if you want to generate stronger cuts, then the idea is to look into not the whole X set, but some smaller parts of it, and actually identify, I would say, minimal sources of infeasibility in our scenarios claimed to be good, but they are not, and kill those minimal sources of infeasibility to do things better. So I will just give you the high-level idea. Unfortunately, I don't have time to get into details. Our preprint is available online, so for those of you IP people especially, you can read the details from the paper. But basically, in that regard, what we do is, these are super weak, so we don't want to use them. So instead, as I mentioned, we want to use minimal infeasibility information. So there is this concept which is known as MIS, minimal infeasible subsystem. So you look at your infeasible problem, and then you identify minimal subset of your model that leads to infeasibility given the candidate schedule. So you can generate better cuts from that. So these cuts dominate the no-good cuts, that's known. But what we know is we can do better than that. So in this work, in a novel way, we propose these things, what we call, named as constraint-based MIS cuts, which helps us to generate in one route, not just one, but multiple MIS cuts, and also in a cheaper way. And in the paper, we also have an LP-based interpretation of these new CMIS cuts. And moreover, we have a way to even further strengthen these cuts that we call extended CMIS cuts. They are also dominating this one. So these guys are the ones that we eventually employ in our exact algorithm. So maybe in 1 minute, I will give you the high-level idea about all of these cutting planes without any details. But as I said, the MIS cuts are, you find the minimal sources of infeasibility. Remember, in the previous slide, in the no-good cuts, I was summing over everything which had this many trips. Here, you are trying to identify a subset, strict subset of the small as possible of a subset of the trips that leads to infeasibility regardless of the rest of the schedule. If you assign these pairs of trips in the schedule, then you are going to end up with infeasibility. If you know that, you can kill these sub-trip structures, basically subsequences. That's what it's doing. But as I said, we do things a little bit better by looking at our sub-problem greedy algorithm solution. We can generate a family of these cuts in an efficient way. And the main idea, very, very roughly, is as follows. So remember, this was our sub-problem, the model, how it looks like. There are a bunch of other constraints here. But if we look at this, we solve this with our greedy algorithm and look at it as solution. So in the solution, remember, these were indicating which trips start on time, which trips don't start on time. So suppose we got the optimal solution of this thing, and this set of trips are the ones in the solution of this model. At the moment, they are delayed. But suppose maybe in my 8-trip example, maybe 4 trips in this set exist, they are delayed. So what we want to do is, we want to pick one of these constraints. Suppose in the example, I pick this one. And by looking at this constraint, this is where the name constraint-based MIS comes from. So by looking at the selected constraints, rather than using all of these trips, maybe 4 of them here, we want to identify, don't read the rest, don't forget about the details, but we want to identify a small subset of it. So for instance, based on the constraint, by looking at this, instead of 4 delayed trips in the current solution, we want to pick a smaller subset, 2 of the trips. And then we take these 2 trips selected, and for each of these 2 trips, we want to identify our pairs of trips that lead to delays for them. So very, very high level. What we want to do is, we want to look at this set of 2 trips that we selected, and for each one of them, we want to find a subsequence of the trips in the schedule that explain why they are delayed. So that using this, we want to, in a logical way, derive some stronger cuts. And I'm going to skip the details, but we have a pretty much a backward propagation type of an algorithm that helps you to give this set. Accordingly, you get a stronger cut, and we even have a version where we can add more information to the cuts to make them stronger. So this was our exact algorithm. So next thing is, again, in a very high level, if you want to solve larger instances, what do? We design an optimization-based heuristic, so in which the main idea is the following. So we have, say, hundreds of trips in an instance. So we want to, first of all, partition them into smaller groups. So say our exact algorithm can handle well, say, up to 40 trips. Then we want to partition this 200 trips into buckets of 40. And then for each bucket of 40, we are going to employ our exact developed algorithm to obtain their exact solutions. But if we have, say, these buckets of 40, 5 groups, we solve 5 of our exact method, and we get their solutions. But now, we need to somehow design another procedure to glue these candidate solutions coming from these buckets of 40 trips to somehow make up a final complete vehicle schedule. Okay, so we want to also devise something. And the problem here is, if you directly use the solutions coming from these 5 different exact models, smaller problems, if you glue them together directly, unfortunately, you cannot necessarily satisfy your service guarantees, service requirements. Because the problem is, here in individual group problems, I am solving my chance constraint model, but individual group chance constraint models might choose different scenarios as bad. So some group for the first bucket, maybe these first 10 scenarios are selected to be bad, but for the last group, maybe the last 10 scenarios are selected to be bad. So if you put them together, all of them are bad now, so I cannot meet my, say, threshold of 90% of the scenarios should be good. So because of that, we basically propose this model, again, very high level, I'm going to give you the idea. So this is saying that for each group, for each partition P in the groups, you need to have their own schedule. But then we add this constraint, which is trying to somehow make their bad scenarios consistent. They are not exactly enforcing exact consistency because otherwise computation is much more expensive. But this constraint is trying to roughly make sure that different buckets are going to prefer different same scenarios as the bad ones, so that when you glue their individual schedules together, I have an overall feasible schedule. And so that's the idea. So basically, this is our scaling up, roughly this picture. We first use specifically deterministic MDVSP to look at the solution and decide how to cluster the trips, create our buckets, groups. And then for each, we solve our exact approach, the exactly chance constraint model, and then we put them together. But we cannot do it exactly like that because otherwise they will be inconsistent. So instead, we use this model and we relax these constraints in a Lagrangian framework and actually solve the Lagrangian dual problem roughly. Okay, so in the remaining couple of minutes, I will just show you again at the high level what type of comparisons we do to justify the value of our model and proposed methodology. Shall I finish, David, with the results, or I should take a pause?
No, okay. Finish it up the results and then we'll take up some questions. Yeah.
Okay, perfect. So we have experiments with few depot options which are realistic, and our exact method can handle up to 80 pretty well. So I'm going to show you these results first. And for each combination, we have 5 repetitions. The chance constraint parameter is 95% of the days we want to be okay with respect to requirements. And for the OTP requirements, 90% of the trips should start on time. And for fairness, for each route, 80% of their trips, they should start on time. And we solve our chance constraint models with this many scenarios, but then we pick a much larger sample to do the evaluation and the comparisons. So I have 3 slides just again to give you high level what's going on. So this is for our exact algorithm performance. As I said, we can handle well up to 80 scenarios. So in each row here, in each level, we are reporting how many instances out of 5 we can solve to optimality in a matter of couple hours. And we see that among the cut options that are used in our algorithm, these are the original MIS cuts, these are our new cuts, these are our stronger cuts. And what we see is if we use our stronger cuts, we are solving more instances. Among the ones that are solved, these are the average solution times. We are ending up with smaller solution times. Among the ones that are not solved within the time limit, these are the optimality gaps. So we are also among the ones that we couldn't solve, we are ending up with lower, smaller optimality gaps. So our method-wise, our cuts are helping us based on what we knew from the literature before. So more importantly, from a practical perspective, would you bother solving the chance constraint model? So here we have comparisons of our chance constraint policy, our schedules coming from our chance constraint model, among the ones that practitioners commonly use, a deterministic model using the average travel time estimates, and deterministic model using the quantile, 75th quantile of the historical data rather than the average. So what do we see here? So when we get these 3 policies, these 3 schedules, and evaluate them with a large sample of possibilities for the future, here on the first part, you see the service requirements, how often they are met. Our target is 95%. As you see, using the average times in a deterministic model is way far from reaching your target of 95. And we are able to pretty much match what we wanted. And on the right column here, you see I'm basing our cost estimates with respect to how much the first option, the average time option, what is the cost of it? On top of it, how much we increase the cost with the more robust solutions. So this one is on the average cost. It is increasing the cost by 8%. We are only increasing the cost by less than 1%, but we are hitting our service requirements, whereas the quantile model is overshooting. It is overly conservative. And it cannot guarantee unless you do a huge tuning effort. But chance constraint, by design, it guarantees you that you are going to get to your target. And finally here, I want to show you how our larger scale case, the Lagrangian-based heuristic works. So in this case, we are considering 200 and 300 trips in this small table. And we have two options for our Lagrangian. So these are the previous methods. Using the deterministic model here, we use buckets of 20 trips and buckets of 30 trips. So in these cases, and let's just maybe look at this one. As desired in the Lagrangian method, the solutions that we get, they are hitting almost our targeted 95% service level, whereas the average one is 19% only you reach. It's terrible, terrible. And in this case, unfortunately, quantile policy is not overshooting. It is not reaching the target, but also the cost-wise, we are not increasing, for instance, compared to the quantile approach, we are not increasing the cost too much, but we are reaching the targeted service level, whereas the quantile one is not able to. So if you're interested in more details, as I said, the preprint of the paper is available online. Sorry, it was a bit fast, but I hope you got the high-level idea and you found it interesting. Thank you so very much for your attention.
And thank you so much, Marve, for your presentation. It's very relevant, especially when we're talking about several practical problems of even e-commerce, but also bus services, public transit, where they start from a depot, finish up all the route, and come back for the repair. So I think there is several applications where we can see them in practice.
Hopefully, yeah, it will inspire some of you.
It's very inspiring. And there are a few questions. I'll take them up in sequential order. One is that, are there any subtour elimination constraints included in the model?
No. No, they are not needed by the design.
By design, okay.
That's a good question, yeah.
Yeah, there was a follow-up. It's like, how would you consider the model when you have vehicle goes on multiple trips in a single operation and back to the depot? Would the model help when the vehicle does not come back to the same origin depot?
No, we have those constraints. So by the constraints, we ensure that the set of trips assigned to a bus, they will end up at the assigned depot. Yeah, we have to ensure that. Yeah, I know the model looks so simple, but if you think about it carefully, it actually is able to ensure all of these things that we have in mind. Yeah.
I think this is one of the earlier slides which you had. How would you make the decision on the delay pairs? Historic data?
On the delayed pairs, like the ones that I know from the get-go? Yeah, we eliminate them. So we add these, what I called valid inequalities, a set of constraints from the beginning to our master problem in the composition algorithm, which eliminates at least choosing, because I can still choose by the delayed pairs. It's okay, as long as I do not exceed the given thresholds, right? But we are saying if you choose too many of them from the get-go, I know that I will exceed the threshold. So that type of constraints we add. Okay. But then at the end of the day, it's up to the schedule. And indeed, in the schedule, you will see some of the trips are delayed. It's okay, as long as not too many.
Yeah. And for the slide where you were presenting the delay cuts, I think Shriram has a question, whether do you add the pairwise delay cuts for every possible pair or you do some cut separations?
For valid inequalities, we do add whatever we have from the beginning. Of course, like if there are too many for you, you can choose a subset. But only for these ones, valid inequalities, we add them from the beginning because it's really helpful because we have an integer sub-problem. We don't want to do so many iterations. So strengthening, actually, by the way, I didn't get the chance to speak, but we have some other enhancements for the master problem from the get-go, which helps. But for everything else, the MIS-based cuts, we just separate in the branch and cut framework. But these guys, we don't necessarily separate. Yeah.
Mm-hmm. A follow-up question from Avinash, I think he asked how we are considering the trip loading, unloading time. It could also vary by shipment and other things. And there's more details on the experiment.
Yeah, that thing is the duration of the trip. It could not necessarily include only the travel time. It could also include the service time, right? If it's a logistic problem, it could include loading, unloading. If it is also the buses, you can also have some other times maybe. So in our model, which is more like stylized, if you will, like it is compactly represented in that single parameter.
That's very interesting. As you mentioned, I was thinking about the electric vehicle. A lot of public transit are now in EVs. So sometimes they have to wait for charging and all. Probably the delay times could be also used for intermittent charging.
True, but if you have electrical buses, like combining vehicle scheduling with charging scheduling, it is a whole different beast. It is, yeah, I have currently actually a recent project proposal submitted in that regard. We are looking into it, but you need to change drastically the model and the approach, I would say so, because charging schedule, if you do it in sequence, you will lose a lot, right? You really want to optimize them jointly.
Yeah.
And charging, there are now also a lot of nice works, but most of them are also limiting, assuming certain charging schedules, like charging profiles. And if you bring in charging, there's also the grid considerations. The cost is not necessarily fixed. It depends how much power you are taking from the grid. So it's a super interesting direction. But this one, we are not considering just to admit electrical buses.
Sure. A question by Animesh. Are skipping less crowded stops or changing routes intermittently dynamically covered in the fairness objective?
No, we are not changing the routes. So no, the network, the timetable, the routes, all that structure is fixed. We are only focusing on the vehicle scheduling, as I mentioned, assigning buses to the depots and assigning trips to buses. So if you want to change different things, you need to, again, drastically change the model. But as far as I know, like most of the transit agencies, indeed, like as I mentioned at the very beginning, they do solve these problems in that sequence. So they first solve a timetabling model for which you can, of course, have an idea, some kind of guidance from the future steps, operational stage, but you solve one way or another a timetabling model, you have the timetable, which is input into the vehicle scheduling problem, which is input to the driver-related scheduling parts. Although there are some works that are trying to jointly optimize, which are very nice, but I think practice is nowhere there.
Okay. Pratik has a question. What are the size of compatible set of trips in experiments? What happens as it grows large? For example, can you look at dense transit with 50K daily trips and all? So how scalable?
No, that's a great question too. Yeah. Okay, that's a great question too. So as I mentioned here, again, I didn't have time to get into details, but I'm happy for the question. So when we create this network flow graph, so this set of arcs in the network, as I mentioned here in quotation, they are compatible arcs for planning purposes. So for now, you can think of, you put all possible ones, but you can potentially do some trimming as suggested. And in fact, in that regard, what we do is something like, for instance, we use expected durations of the trips and then do something like to speed things up a bit. And it's reasonable that if certain trip pairs are looking incompatible when you use expected travel times, we don't put them there, which helps because at the end of the day, they probably will not show up in the schedule. And I mentioned expected as an example. You can again use a different statistic there, but using such ideas, thinking that certain things will not likely to appear in the optimal solutions, you can actually reduce the number of arcs from the beginning, which will help tremendously. Or you can think of some maybe gradual process, right? You start small, you get a schedule, and almost like a column generation, you keep generating maybe more improving options later on. That's also possible. But it will help a lot, especially for large scale cases, if you can make the graph from the beginning smaller.
I think a question is more about, can we have heterogeneous fleet, for example, with different capacity and all? I think that should be okay, right? Because all we're looking at is flows here.
Good catch. In theory, yes, you can modeling wise, but we are leveraging the fact that our fleet is homogeneous.
Yeah.
So in the network flow model, it doesn't matter which bus per se a trip is assigned to, and we are leveraging it. If you have heterogeneous buses, you need to keep bus indices around.
Yeah, you need to track that. Yeah.
It's a good catch. So no, it could be limiting actually if you want to move to that direction. It's doable. I'm confident it's doable. The ideas are extendable, but indeed we leverage the fact that we have homogeneous buses.
Great. No, I think we kind of answered all the questions, Marve, and we are very fortunate to have this talk today. And I think
my pleasure.
Audience kind of enjoyed the conversations and the discussions. So thank you so much for presenting on our forum, and we hope to host you again sometime soon.
No, it was my pleasure. No, it's so much fun.
Thank you
very much for having me.
Thank you all the participants for joining this evening.
Thank you very much for attending.
We're very excited. Yeah, thank you again all. Thank you.
And if anyone has any questions, feel free to email me or let me know. I'm happy to chat always.
Thank you so much. Thank you.
Okay, let me stop sharing. Thank you.